presentation on nanochemistry or nanotechnology. An issue is becoming more and more critical every day. Our guest has received his graduate degree in inorganic chemistry from the University of California, Los Angeles. He was a founder leader of the University of California, Berkeley Global Science Institute. On research focuses in using the principles of reticular and material chemistry for applications in clean energy, health and environment. He has authored more than 40 publications, including 5 in Science or Nature Family journals, with over than 15,000 citations. He is now the Executive Director for Scientific Research in the Royal Scientific Society and the Assistant to Her Royal Highness Princess Sumaya bint Al-Hassan for Scientific Affairs. Please join me in welcoming Dr. Cordova.
Okay, and so this is a very famous picture by an artist named Escher, and this is a joint right here. And this joint and this joint, which is in the shape of a cube, these cubes are connected by a link. And so we have to use our chemical knowledge to figure out how do I find the chemical. And so as chemists, as nanoscientists, we use the periodic table of elements as our library to make these clusters, these building blocks. So every element that you see in blue, we are capable of using as a molecular building block for a joint. Okay? Now, we have the joints. We have to connect the joints by a link, right? Exactly. So we use what's called organic chemistry to build organic molecules that connect the two joints. What I want to transition now to is that's the chemistry of these materials. I want to talk about what are they good for? Why do these matter? Why should you care? And so because of the actual structures, we're able to not only create new structures, new chemistry, but also have applications, right? And from the metal clusters of the structures, you can have reactivity, you can do things like catalysis. Catalysis means basically you transform one molecule to something more value added. You can do gas absorption, separation, etc. Well, let me show you this animation. And you see that there's no walls, right? It's all of these organic clusters connected by organic linkers, and everything else is empty space. So that means if I'm a guest molecule, if I'm a molecule, I'm coming into this material, I can go anywhere in this structure, right? And that's very important. I'll tell you why in a second. And so if I take 1 gram, so this material, if I take 1 gram, everyone knows what a gram is, right? If I take a tablespoon of this material, and I was able to unravel it on the molecular level, I have the same surface area as a football field, okay? We're talking about 10,000 meters square per gram of that material. That's pretty crazy. That means on the nano level, the atomic level, I have all of this free space in 1 gram of this material. And finally, I don't think I have to talk about water in Jordan, but everyone in Jordan knows that there's major challenges when it comes to securing fresh, clean water in the future. So I'm going to show you how these materials apply to each of these molecules, right, for the benefit of society. First, let me show you a small little video so that you can visualize on the nano level what's happening here. And so this is a small animation. These are nanoparticles of the MOFs that I was telling you about at the beginning. And we're going to zoom in really close and carefully on one. And so you see the nanoparticles are cubes. They can be any shape you want. But here is one nanoparticle in particular. If we look at the atomic level now, you can see all of the free space, and you see these gases sort of coming around, and they're somehow attracted to the free space of the MOF, and they come inside and they're stored there for whatever use you would like.